The last topic in our note pack relates to catalysts. Catalysts are those things we add to a reaction to speed them up. Not a reactant, not a product. They're there to alter the pathway. Nature has enzymes as biological catalysts. If a catalyst is added that's in the same phase as the reactants, we call them homogeneous. If they're all gases, liquids, solids, aqueous, if all the adjectives in the equation are the same, they're termed homogeneous. If a catalyst is in a different phase as the reactants, some are gases, some are liquids, different adjectives if you will, they would be known as heterogeneous catalysts. The way a catalyst works is by altering the pathway. What it will do is actually provide a different set of collisions, a different mechanism, different sets of elementary reactions with the ultimate goal of lowering the activation energy. Thinking that through in terms of a diagram, if reactants form products, and this would be representing a single elementary reaction, there is a barrier called activation energy that separates reactants and products. If I can provide an alternate pathway that would lower the activation energy, we would then speed up the overall equation. What's important to note is that reactants to products, the overall change in the reactant product delta E or delta H for heat of reaction would be the same even if the pathway took to the top of the hill or just a different pathway with that catalyst. It doesn't change the overall energy of the equation, but it does lower the activation energy barrier. Let's take a look at an example that I've written. I have H2 plus ICl makes HI plus HCl. I'll call that step 1. Step 2, and these are elementary reactions. HI plus ICl gives me I2 plus HCl. If this are a proposed mechanism, a two multi-step elementary reactions, let's write a balanced equation for the overall reaction. I can do that by simply adding together to find the overall equation, simplifying anything I can from the left to the right. What I notice is that HI is formed here and then made here. Something that's formed and then consumed in the next reaction is known as an intermediate. It does not appear in the overall equation. So here's what I'm noticing as the overall equation. I have H2 plus 2 molecules of ICl forming I2 and 2 molecules of HCl. The overall equation eliminated the intermediate HI. The rate laws for each elementary reaction would simply look like this. For the first elementary reaction, we would write rate is equal to K times the concentration of H2 to the first order times the concentration of ICl to the first order. The second elementary rate law would look like rate is equal to K, and this could be called K1 and K2 if this represents K1 and K2 for our elementary reactions, times the concentration of HI times the concentration of ICl. The intermediate appears in the elementary rate law. It does not appear in the overall equation. So we've written the rate laws for each elementary step. If the first step is slow and the second one is fast, what rate law do you expect to be observed? If the first step is slow and the second step is fast, what is the rate law we would expect to be observed? The rate law comes from the slowest step. The observed rate law would indeed match the first elementary reaction. If the first step is slow, it gives us directly our observed rate law. So rate is equal to K times the concentration of H2 times the concentration of ICl, first order with respect to both reactants, second order overall. When the first step is slow, that gives us directly the observed rate law. Now let's compare this to a second example I have written down below. Here we have a molecule of peroxide, H2O2, plus I negative, forming water, and IO negative. IO negative then reacts with H2O2, producing water, and I negative. We have some overall equations to consider. The overall equation is simply adding together both elementary reactions, simplifying what we can. What I'm noticing is a couple of interesting things. First of all, I have IO negative 1 formed and then used. IO negative 1 is what we called an intermediate. It's produced and then consumed. What I also see is that I negative appeared as a reactant and again as a product. I negative is a reactant in step 1 and appeared unchanged as a product at the end. This is known as a catalyst. Not a reactant, not a product. It simplifies out of the overall equation. It's something I added to alter the pathway to create a faster first step. The overall equation shows 2 units of H2O2 forming 2 molecules of water, and the rest has simplified out. I forgot to write O2. I'm not balanced. Sorry, I missed writing an oxygen in that second elementary step. I had to go back and add that. Peroxide breaks down to give water and oxygen. Oxygen O2, water and I negative should have been written here in my example. Adding that back onto the overall equation produces a balanced equation for the decomposition of hydrogen peroxide. What it allowed me to do is to review what an intermediate is, something that's produced and then used, and the term catalyst, something I add and then get back at the end unchanged. The catalyst is I negative, the intermediate is IO negative 1. And if the first step is the slow step, comparatively to the second step, which we could say is faster, the observed rate law comes from the rate determining step. Rate is equal to K times the concentration of H2O2 and I negative. The catalyst appears in the observed rate law. It does not appear in the overall observed balanced equation.